What do physicists think about controversial topics like interpretations of quantum mechanics, fine-tuning, the information paradox, cyclic universes versus inflation? Well, stay tuned because we are going to reveal a major new survey of leading physicists and what they think about these and other topics. And some of the results are quite surprising. So joining me to announce and explain the results, I have my co-author on this survey paper, and he's also my co-author on our upcoming book, The Battle of the Big Bang, New Tales of Our Cosmic Origins, Niayesh Afshordi. Niayesh is an award-winning astrophysicist and cosmologist at the University of Waterloo and the Perimeter Institute for Theoretical Physics. So welcome, Niayesh.
Hello, nice to be here. Good to see you, Phil.
Good to see you. So a little bit about the survey. Last year, Niayesh messaged me and said there's going to be this amazing black hole conference in Copenhagen. And Niayesh, why don't you say a few words about why this conference was the absolute perfect place to do a survey like this?
Yeah, so this was a conference in Niels Bohr Center for Physics, or Niels Bohr Institute. And Niels Bohr, of course, was one of the primary figures in modern physics and one of the pioneers of quantum mechanics, and he was in Copenhagen. So Copenhagen was, in fact, historically very important in physics, where basically the first interpretation of quantum mechanics was developed. So, and now, of course, black holes are hot now. Everybody is excited about black holes. We have lots of observations. So this is the topic of the day, and we have some of the leading physicists and astronomers who worked on black holes gathering together in this hub for theoretical physics, and they're trying to think about what's the future of quantum mechanics and black holes and how they come together possibly. So there were many leading physicists, young physicists, and more senior researchers there. And I thought it would be a good opportunity to kind of get together, talk about it, and then maybe get a temperature of what everyone is thinking about where the physics is going.
Right. So I thought it was great because, you had experimentalists, you had theorists, you had astrophysicists, you had cosmologists. It was a really eclectic selection and some of the absolutely top names in the field. So just to be clear, we don't think science is decided by opinion polls. It's decided by data. But I think surveys can be useful for historians and science communicators just to know, what's the consensus of a field actually is at a given time. So let's jump straight into it. The first 4 questions are related specifically to black holes. As a black hole conference, but I'm going to leave that till last and start with a second section, which is about fundamental physics, topics like interpretations of quantum mechanics, dark matter, fine-tuning, and so on. So the first one, suitably because it was in Copenhagen, was about the correct interpretation of quantum mechanics. So let's have a look and see what the results are. So here we go, and no surprise, we're in Copenhagen, and Copenhagen was the lead. What do you think about this, Niayesh?
Well, I mean, I think people are impacted by their vicinity, I suppose. It was a good environment to think Copenhagen is the right answer. But of course, as you see, most people didn't have an opinion. What is even more than Copenhagen?
That's true. Yeah, that Copenhagen was the leading interpretation, but yeah, no opinion was more popular. Does that mean physicists are pretty conservative?
Well, there is this, I guess, this wording that people use, shut up and calculate. So I guess that's what no opinion means.
Right. But what's interesting, I think, is it is pretty consistent with some other surveys that Copenhagen and many worlds are the top 2. And we see that in our survey, and that has been shown in previous surveys. But let's go to the next topic. So obviously there's different candidate theories for quantum gravity. So we see here string theory is the leading pick out of the theories, but yet again, if you pick other and no opinion, you put those together, actually they're actually majority view. So was there any surprises here? What do you think about this, Niayesh?
Yeah, it's interesting that I guess people, the participants of this conference, were more agnostic about the fundamental physics, be it interpretation of quantum mechanics or quantum gravity, neither of which have direct experimental tests for them. I think one thing is asymptotic safety is actually more popular than loop quantum gravity.
Yeah, that was a surprise.
And I think I have a guess as to why. I think they have a hub of asymptotic safety, or this new hires in asymptotic safety over there in Copenhagen. So that could
Ah,
be part of it, that there were more proponents of it. But I think all in all, uh, uh, basically most quantum gravity practitioners kind of stick together, people who don't do a string theory. So they kind of work together, people in loop quantum gravity, asymptotic safety, or even causal sets and others. So they kind of work amongst each other. So maybe you should kind of add together those votes. I'm not sure what it would be, but maybe it becomes competitive to a string theory.
right. I mean, I think the interesting thing is some people have said string theory is the only game in town. And definitely the people at the conference who answered the survey don't seem to agree with that. So I think that is of interest.
Absolutely.
But let's move on to the next question, which is dark matter. And here, um, I think the most popular one here is clearly the hybrid. So, I mean, I guess like regular matter, there's different, regular matter is not just one thing. We have protons and neutrons and electrons. So I guess the community is saying they don't think dark matter is one thing either, because hybrid is the most popular.
Yeah, I mean, I think I think the audience had mixed opinions here. They were not entirely sure. I mean, one interesting thing is primordial black holes is very popular. I think, is it the most popular after
Yeah,
the hybrid option? And
yeah.
I guess
For one particular option, it is the most popular.
yeah, and I mean, this was the black hole conference, so maybe that's the explanation.
Right.
Maybe the
Yeah.
black holes could explain dark matter. But I mean, another thing you notice is that WIMPs, this heavy particle dark matter, used to be the favorite up
Mm.
until maybe 10, 15 years ago. But in the past decade, the light particle dark matter has kind of risen in popularity, partly because people didn't find evidence for WIMPs, but also because of other theoretical developments by, say, string theorists who kind of advocated maybe axions is the way to go. So yeah, that's clearly seen in this poll as well.
Yeah. I mean, why the shift away from WIMPs, do you think? What was the development exactly?
Yeah, I mean, I think part of it was frustration that there have been these searches for WIMPs for maybe 2, 3 decades, and they all came up empty. But there are also basically some theories that thought maybe before there were theoretical motivations to look for WIMPs, and not as much maybe for axions or light dark matter. But then there were a few papers maybe 10, 15 years ago that suggested maybe there are expectation of seeing this light dark matter, because I mean, light is, you always think in physics getting lighter particles are harder. There's this kind of tendency about naturalness that it's easy to get heavy things, and light things you have to work hard, you need symmetries and things like that. But yeah, it turns out that there have been a few papers and a few leading theorists in the past 10, 15 years who suggest that maybe it's not that hard. And then the community, because they were kind of frustrated with the heavy ones and couldn't find anything, just moved away.
Yeah. And I guess the other thing that was interesting here was virtually no support for modified gravity. Although I guess when we said hybrid, there are some models that have a hybrid between modified gravity and particle dark matter, like Justin Corey suggested one. So was that a surprise to you, how few people voted for modified gravity?
It's not that surprising. I mean, modified gravity generally is not very popular with practicing astronomers and physicists, because it's very hard to fit data, in particular cosmic microwave background data, which is kind of the gold standard in cosmological data analysis. So that's not very surprising to me. But yeah, indeed, there are a lot of options that are hybrid. So it would be hard to kind of list all of them here. And yeah, every one of them may have one or two proponents.
Right. All right. So let's move on to actually the topic of our book, because our book, Battle of the Big Bang, is about these competing ideas for the early universe. And inflation, like with string theory, some people might think it's the only game in town, but we suggested some other options. And again, I think obviously it's much more popular. Cosmic inflation is much more popular than string theory is in quantum gravity. But nevertheless, it looks interesting to me that in neither case does it actually get majority support. So again, that was sort of surprising to me. I thought it would cross inflation would cross the 50% mark and at least have the majority. But it doesn't seem to do so here.
Yeah, and partly maybe it was an eclectic audience. It wasn't a cosmology audience, and if you had a cosmology audience, probably the answer would be different. But this audience was kind of more open-minded because they were not practitioners of cosmology and inflation. But if you kind of get into cosmology conferences, people who do early universe almost exclusively do inflation. So I imagine probably would get a different answer then.
Right, yeah. I'm sure if you surveyed everyone that worked on Planck, the spacecraft that mapped the cosmic microwave background, you'd probably get a higher number for inflation. But, these are people who are, at least, they're not early universe cosmologists, but, they are presumably reasonably well informed about the topic. They are astrophysicists and cosmologists. So to me, it was a bit surprising that it didn't cross the 50% mark. But it is clearly, I've always thought of it as the leading horse in the race, but far from crossing the finishing line. I
think that's great. There is a lot of open-mindedness for people who are somewhat objective, somewhat basically somewhat outside the direct field. And I think this open-mindedness is a very good thing because then new ideas can be explored kind of more broadly.
Yeah. So now the next question is the one I would say most nervous about. And that's because in our book, we wrote that cosmologists today don't really think that the Big Bang was necessarily the beginning of time. And we said that's what probably is the consensus view of cosmologists. And we wrote the book. And then I thought, well, let's survey the scientists and see what they say. And it had they said something very different to what we would say, is we were going to have a lot of egg on our face. But fortunately, this is a very interesting result, I think, because what we did was we asked physicists, what do they think the term Big Bang means? Because some people might think it means, the theory that says there was a beginning of time. But the alternative, what we said in the book, was no, it's just a theory that says the universe evolved from a hot, dense state. And it says nothing about whether there was a beginning of time or not. And Niayesh, were you relieved to see that this is indeed the... we actually have an answer with the majority view, which is kind of rare in this survey.
That's right. This is, in fact, the only answer we have a majority view, which is interesting. So, indeed, there is a strong consensus. Well, I guess it's still not exactly a consensus, right, but this is the only option in the entire survey where was a majority answer. So it was kind of striking.
Yes, yeah, and a relief for us, I guess. But yeah, I think it's very important because we do get a lot of popularizers and people saying that Big Bang is a theory that says the universe had a beginning, and what we're saying, and fortunately our colleagues agree with us, saying no, that it's a theory that says the universe evolved from a very hot, dense state, and what happened before that, maybe it was the beginning, maybe not. The theory doesn't really say that. So there's another topic that I think is very interesting, which is the claimed fine-tuning of the constant of nature. Physicists often refer to this as anthropic coincidences, whereas people in philosophy often call it fine-tuning for life. But what do you think is interesting here? That basically we've got, we gave them quite a few options. The values could be set by necessity. There could be brute facts that don't need any further explanation. It could be explained by a multiverse, explained by a Darwinian process, or an intelligent designer. And the most popular one is that they're brute facts that don't need any further explanation. Now, I think that's actually your view, wasn't it, Niayesh? I remember interviewing you quite a few years ago about this.
Yeah, I don't think I ever had a very strong view on this. I'm just it's hard to get convinced by any. I know a lot of people who do have a strong views on this, and then I've never found them convincing. So I have been always on the fence on anything that's very strong. But it's kind of surprising that people don't worry about anthropic coincidences. And I think part of it might be, again, it was very popular maybe 10, 20 years ago, because basically what happened was the string theory couldn't explain parameters of universe we see around us. And I think some of the proponents of a string theory decided that maybe everything is anthropic. So that became popular very much. just because of these few handful of people who did that. But then I think they have all moved on, and the string theories are not interested in explaining the world anymore.
Right.
So yeah, and I guess then that has subsided, it appears.
Yeah. Also, two other things I think are interesting about that one is that let's pull the results back up actually. So one is that the brute facts is the most popular one, but that was also exactly what there was a survey of philosophers called the Field Paper Survey, and there was a remarkable concordance. We had 33% of our people that answered the question pick that, and the philosophers had 32%. So, and it was also their most popular option. The other thing I think is interesting. We're often told that you have to pick between a multiverse or an intelligent designer, maybe a deity of some kind, to explain these puzzles. But both philosophers and physicists reject that dichotomy, that really we don't need to pick either one of those. Although in our survey, the multiverse was certainly more popular than the philosophers. It's sort of the second most popular answer. But
I guess just to add that maybe this kind of goes to say the power of Occam's razor, that it seems that, neither of those explanations, either an intelligent designer or multiverse, they cannot be really tested in very satisfactory way. So the simplest explanation is it is what it is.
Right, exactly. Yeah. We should do a survey on the really important topic of should we pronounce it multiverse or multiverse? But we'll probably have a transatlantic divide there. But anyway, let's go on to dark energy. This was another one. The standard view is that the universe is accelerating its expansion, and it's caused by a cosmological constant. But yet again, although we find here that it is the most popular of all the options, yet again, it doesn't cross the sort of majority threshold. Isn't the standard model of cosmology saying it's a cosmological constant?
It does, and indeed that's the standard, but I guess it leaves a lot to desire, and I think 70% of people, or is it 60% of people, desire something more, apparently.
Right, and there have been hints that dark energy is changing over time, so it wouldn't be a cosmological constant. So stay tuned, because we're going to be announcing new results from DESI. I don't know exactly when we're going to release this video, so it may have already been released. I actually know the results, but I can't tell anyone because they are embargoed. But we've recorded.
I tried to get him out of him, but it didn't work. So
no, you're gonna have to offer me a lot more than what you offer me to get the results. Maybe a couple of drinks at the bar, and I'll spill the beans. But yeah, keep your eyes on this channel, because we will have the new DESI result. DESI is the Dark Energy Spectroscopic Instrument, and they've got their 3-year data either about to be released, or it will have already been released, depending on when we release this video. But so far the hints are that it's actually changing over time, so it wouldn't be a cosmological constant, and we're going to see with the 3-year data whether that holds up or not. All right, so let's go to the last question in the fundamental physics section, which is about this thing called the Hubble tension. Niayesh, why don't you just explain what is this Hubble tension?
So there are a lot of things in the cosmos that we can observe that tells us about the expansion of the universe over time. And they're all very mature and powerful. Over the past 50 years or so, we have kind of measured all of these better and better over time. But we've kind of had hit a conundrum that there are two basically very powerful ways of measuring how fast the universe expands. One is based on observations of early universe, like cosmic microwave background and baryonic acoustic oscillations. And another is just directly measuring the expansion by observing stars in our vicinity, or galaxies that are not very far away from us. And it seems that they end up with different answers that are now significantly discrepant by about 10% or so. So the rate of expansion of a universe, depending on which data we use, appear to give different results, and they cannot be statistically compatible with each other. Does that mean that our interpretation of cosmology, as we have, is wrong, or does it mean something else? Maybe there is something wrong with the measurement of stars and galaxies in our vicinity. So that has been a very hot debate for the past decade.
Right. And so basically the big issue is there new physics needed to describe this, or is it some error in the observations? And it looks like the most popular view is that it's an error in the supernova data. How do you feel about that? Is that something you expected? I know you had a bet with David Spergel, who was one, your PhD advisor, and two, the lead theorist on NASA's WMAP spacecraft. And he thinks that this is the most exciting thing in cosmology, right?
Yeah, I mean, I think he said that at some point. I'm not sure if he agrees that anymore, but he wanted to be a contrarian, I think. And so he said this bet with me. So I think over time he's also kind of coming to this idea. But to be honest, I mean, if there is a systematic error in supernova data, someone needs to point it out, because we haven't actually been able to find that systematic error. And the interesting thing is that the same group, or at least one of the leaders of the same group that discovered dark energy and won the Nobel Prize for it, is actually the same person who is leading the analysis for the supernova data. So clearly he's angling, so that's Adam Riess, he's going for a second Nobel Prize. But whether it's going to happen or not, I guess we're going to find out.
Right. And I guess the money at this conference is not going to happen. But we shall see, because as you say, no one's actually found what the error is. And it's presumably a lot of leading experts would love to find that error and would point it out if it was obvious.
That's right. It's not easy to find that error, but also astrophysics is complicated. So even the best astrophysicists can be wrong and have historically been wrong. So I guess we'll find out.
So now we're going to go to the black hole sections. Black holes are obviously absolutely fascinating. And there's also plenty of controversies about what's going on in black holes. And perhaps the most popular controversy is this thing called the information paradox. Maybe before we go to the results, maybe just to unpack, Niayesh, what is this information paradox?
Right. So about 50 years ago, Stephen Hawking, the latest Stephen Hawking, that was one of maybe the most famous, possibly the most famous physicist of our generation. He did a simple calculation that if you apply the laws of quantum mechanics, which have been tested by 50 years basically back then, when he did the calculation, and apply it to black holes, which again was a theory of general relativity, prediction of theory of general relativity was very successful. At the time, black holes hadn't been seen yet. That was in 1970s. But they have been very well established as a solution of Einstein's theory of gravity or general relativity. So Hawking tried to apply basically these laws of quantum mechanics to black holes, and he came up with something very surprising, that black holes cannot really be black. They would actually emit light or light particles. It could be neutrinos, it could be gravitational waves, or it could be photons. And they have a tiny temperature. It would be very hard for our detectors right now to see them. But if you leave a black hole in vacuum for a long time, eventually, in fact, it would evaporate. It's because it has a tiny temperature and it slowly basically emits light, and eventually it would just go away. But then the puzzle was information that fell into the black hole, into the event horizon, which according to Einstein or general relativity, nothing can escape from. What happens to that information? I mean, if the information can get out, that means that something is traveling faster than the speed of light. And if the information is stuck in, so then what happens to it? So this is known as a black hole information paradox. And in fact, we are celebrating the 50th anniversary of that. So there's a workshop in Stony Brook that we're organizing in this fall. And it's been kind of one of the most dogged paradoxes in physics, which brings quantum mechanics and black holes together. And they're two of the most interesting hot topics. We still, on a daily basis, talk about both of them. And there is this deep mystery about combining these two and what happens to information. Yeah.
So is it right to say, basically, it looks like general relativity, at least at first glance, says information cannot get out of a black hole or is destroyed by the black hole, I should say.
Yeah.
And quantum mechanics says information can never be destroyed. So that's the paradox.
That is the paradox. The quantum mechanics cannot destroy information. Yeah, go ahead.
Right. So let's see what our survey said. So what I find interesting here is, so it is right that the respondents do think that information is preserved,
That's right.
But what I think is interesting is that there is at least a significant minority that think it's irretrievably lost. And a lot of the media have been saying, well, everyone agrees that the information is preserved, but they don't agree as to how. But it seems here that that's actually not true.
So they're actually within a statistical error of each other. So I would say, I mean, I wouldn't even assign like which one is bigger than others because they're just comparable
Right.
from just a statistical point of view. So it seems that like people cannot decide, yeah. So whether information is lost or comes out in Hawking radiation or just stuck in something. So the remnant is something that's kind of left at the end of Hawking evaporation. Yeah, so I think it's still a paradox.
Right. And not solved despite all the headlines that you will often see in the media.
That's right.
Information paradox solved. Clearly, the physicists at the Black Hole Conference don't think so. But let's go on to the next black hole topic. So basically, there are these supermassive black holes, and they have what kind of masses are we talking about in supermassive black holes?
Yeah, so we have masses like millions of solar masses, like the black hole at the center of our galaxy, Sagittarius A star, to many billions of solar masses that we see in big galaxies like M87, the first black hole that was ever imaged, and other black holes we see even with JWST or at high redshift. So yeah, these are huge, gigantic black holes, and it's the big mystery how we make them.
Right. So let's have a look at what our survey thought about how they were made. And the most popular answer is they are direct collapse seeds. Now, why don't you explain what are these direct collapse seeds?
Right. So these black holes are giant, and the only kind of black holes that we know how to make in astrophysics in a conclusive way are like stellar black holes. If you have massive stars, they run out of hydrogen, they burn all their hydrogens, and eventually they kind of start burning helium and carbon and other heavier elements until they get to iron. And if they're massive enough, that's where they kind of collapse to form, to have a supernova explosion. And whatever is left of that could be a black hole if it's a massive enough star. But those black holes that come out of stars, at most they could be tens of solar masses. But the question is, how do you get from tens of solar mass to millions to billions of solar masses? And the astrophysical process, you can imagine, they have their own limits. So you cannot kind of grow black holes arbitrarily fast. And you have a finite age of the universe. We've measured the age of the universe is 14 billion years or less than 14 billion years. And the question is, okay, how can you grow black holes so fast within the age of the universe from tens of solar masses to billions of solar masses? And there is a big controversy that there are basically two camps. One is saying that somehow you don't start from tens of solar masses. There are some new types of black holes you could make from direct collapse of these heavy clouds. So there's basically, instead of forming a star and having a supernova explosion and so on, somehow in the early universe, you have some big blobs that could directly collapse into a black hole instead of forming a star. We haven't seen any of them. But if you don't think black holes can grow fast enough, then that's really the only option. You should just make them big to begin with. The other option is that maybe black holes can grow fast. These are known as super Eddington accretion, that somehow there are some exotic way of feeding black holes that can make them very big, very fast, basically fatten them up. And yeah, I mean, this is still a controversy amongst the astrophysical community.
Right. Okay, so let's go to the penultimate question here, which is the fate of matter as it falls into a black hole. What actually happens to it? And here's an interesting result that actually it's crushed into a singularity. Is still that is the classic view. That's what you will see in a textbook. And I think yet again, like with string theory, like with inflation, like with the cosmological constant, the classic view is still the most popular view, but yet again doesn't cross any 50% threshold. And weirdly, and maybe you can explain this to me, in the Big Bang, very few people thought that there was a singularity at the Big Bang, but it seems to be at least more popular here for the black hole. Why do you think this discrepancy?
That beats me. Uh, yeah, I mean, I suppose that maybe because people haven't thought as much about this. I mean, the one thing about Big Bang is that we could, I mean, there's a lot of observations that probe the Big Bang, so maybe we
Yeah,
are hoping that we can probe the nature of whatever happened. Maybe there was a bounce or something else. Um, but and we do probe basically a lot. Like inflation is a model which make predictions. It's not the only one, but nonetheless. In the case of what's inside the black holes, things are, I guess, much more complicated because we don't really see what's inside. So I guess people just maybe are stuck with the Occam's razor, which is okay. The simplest is the singularity, even though it may not make sense. We just,
right.
yeah, they don't
Yeah.
really have other preferred options, looks like.
Right. And in fact, of course, we're hoping, that a quantum theory of gravity will explain both the Big Bang and what's in black holes. And there has been a suggestion that we could maybe test theories of quantum gravity with black holes. And that was our very last question here in the black hole section. So let's have a look at what was the most popular answer for how we could test quantum gravity with black holes. And the most popular answer is this one: effective field theory corrections to in spiral ring downs. Can you explain what this means? I don't think everyone's going to know what that refers to.
Yeah. So basically, the idea is that there should be some tiny, small corrections in the gravitational wave signatures that we find. I mean, LIGO has already detected gravitational waves from hundreds of black holes, and black holes binary mergers. Basically, these are two black holes that are spiraling around each other and then merge together and emit gravitational waves. So I guess the suggestion is that maybe we're going to see tiny deviations from the general relativity predictions for these gravitational waves, and those tiny deviations will tell us something about the nature of quantum gravity. I think this is one of those examples the majority opinion is probably wrong.
So what do you think is going to happen?
I think my choice was the least favorite one. Those are the gravitational wave echoes, which are basically the kind of waves that could go basically fall into the black holes, but get reflected possibly from quantum structure near the horizon and then come out. And I think to me, that seems
Actually,
like a much more convincing way of going at this.
actually, there's something interesting there because we put out the survey and a few people tick more than one box. So I decided we're going to exclude those because it's not really fair if you have more than one box. But in the appendix in the paper, we have got the results when you include those, and there the black hole echoes jumps up quite a lot
Oh, it
in
does. Okay.
popularity. It
Good,
does.
good.
It does. So maybe if you give people a few more sort of votes, they're happy to go with your preferred option. So
Okay.
we will see what happens because presumably, we have LISA launching next decade, and which is the space-based gravitational wave observatory, and who knows what it will see. And then it would be really interesting to come back, as we get more data, to see, how opinions change. Hopefully, if science is doing what it should do, as the data changes, opinions should change. So that would be something fascinating to do. But obviously, we've got a few more years yet. But I will say, just before we finish up, that we are partnering with a large organization. And I don't want to say who yet because it's not all confirmed. But they're going to rerun this survey with a much, hopefully, larger population. So we'll have maybe higher statistical significance. Now, they won't all be like top names in the field, which I think we got from the Copenhagen conference. So it might be interesting to see, are there discrepancies? But that's what we have to look forward to. So any final thoughts, Niayesh, before we sign off?
Yeah, so I just wanted to add that a lot of the compilation of this data was done with by my PhD student Alice Chen, who is very busy studying for exams. So I didn't want to disturb her for
Right.
this discussion. But yeah, so it's going to be fun to see basically people's reaction to this opinion.
Right. So if you have your own reaction, please leave them in the comments. If you like this video, give it a like. And we'll see you next time when we have some interesting science results.